explaining dual decompositions for parsing in NLP, this article, MRF optimization via dual decomposition. I mean, this article in 27, which is one of the first articles that uses dual decomposition for Markov random field optimization. So until now, we've talked about duality and those things, but this is different. This is dual decomposition. And so dual decomposition leverages the optimization that complex inference problems can often be decomposed into efficiently solvable subproblems. The things that we do in optimization, for example, if you want to optimize minimum of f of x, we decompose the variables into x1 and x2. And so each one in itself is easy. So we just need a coordinator to relate these two things. That's saying that we should add these two subproblems. So this coordinator or master has some slave 1, slave 2 here in this case, and you can decompose the problems. And this master is a coordinator. It says that after solving these subproblems, at the end of the day, you should add them. So block coordinate block coordinate descent uses a decomposition or partition. Of course, they didn't use this block coordinate descent. I just used this slide because it is interesting that to notice and be aware that block coordinate descent is just a kind of decomposition. And so in primal decomposition, you decompose in the domain, and x1 is in your click 1 and x2 is in 2 clicks. So we have 2 clicks, for example. We decompose them. And as I said, we name our first subproblem to be slave 1. We name our second problem to be slave 2. And this is the master that knows that they should be added together. And so the dual decomposition of this could be written as these are the constraints. So Lagrange multiplier, this is the summation of the two functions. And we can solve the subproblem and also the second subproblem. This is another example. Sometimes you have a z variable that is somehow shared between them. So no problem. Again, we can use, say, that f of x z1, g of y z1. And this makes sure that they are equal. If z1 is equal to z2, then our constraint is satisfied. So this is our constraint. We make sure that this z variable is satisfies both this area and this area. So that's why we need this constraint. So the assignment problem, you know that this is the unary potential, binary potential. You have seen it several times. So we want to minimize this energy, Markov random field energy. And there are 2 classes of methods. You can either use graph cuts. I've explained graph cuts in one of my papers and also my playlist for approximation algorithms. Message passing, you're familiar with message passing, so any of these methods could be used for that. So in previous lecture, you saw that we want to minimize this energy, or let's say to find the parameters of Markov random field. And for map assignment of Markov random field. And these are the constraints that we need to know for consistency. I've explained why we need them. And that is the master and slave configuration. So this picture is from this article. And so the coordinator knows how these subproblems are related to each other. So the main idea is first we decompose their original complex problem into smaller solvable subproblems and extract a solution by cleverly combining the solutions from these subproblems. What the subproblems will be, as well as the so-called master problem that will act as a coordinator between the slave problems. In addition, one can either decompose the original problem, this is the primal decomposition, or its Lagrangian dual, that is the dual decomposition. So any of them. For dual decomposition, you will see that we decompose the problem instead of just two blocks. There are several blocks. We add all of them, and we relax them, and we form this Lagrangian dual. You see, when xi is equal to x, our constraint is satisfied. And so this is a subgradient of Q. So this is a master and slave that I explained. So we solve the slave Markov random field using max product, wave propagation. We compute it easily. But we update the parameters for slave Markov random field using x bar t. For example, this relation that is proved in the lemmas. And these are the updates.